Sorry, I had to cut the last video. So I left you talking about viscosity and how magmas that have more silica tend to be more viscous and hence have low flowability or low flow velocity. So typically, magmas that are ultramafic or mafic in composition tend to flow quite fast, like the ones that we see in many Hawaiian eruptions, for example, because of their low silica content, right? Again, high silica, high viscosity, so low silica, low viscosity, high flow velocity. So magmas that are felsic in composition flow very slowly due to their silica content. Again, same idea. So these are not very common flows, the felsic type of flows, but I'll show you some of the examples where it does occur. The important thing to take away in this message is, again, with high silica comes high viscosity and in turn low flow velocity. Another important thing to point out from this diagram is that the temperatures at which the magmas form. So typically the ultramafic and mafic magmas form at higher temperatures of about 1,000 to 1,250 degrees Celsius. And those of felsic nature form at cooler temperatures at about 650 to about 800 degrees Celsius. So again, usually the way I think of it is the darker the color, the less silica, the higher the temperature. Okay? So hopefully you create your own way, but higher color means higher temperature, means lower silica, means more mobility. So this is the second way in which we classify igneous rocks, which is based on textures. Many inferences related to rock's origin and history can usually be made on observations of the rock's texture. Overall, its appearance will be based on the size and the shape and the arrangements of the mineral grains that it has, not on how it feels. So texture in geologic terms differs from texture in what we more culturally know as texture. Okay, so texture really relates to the size, the shape, and the arrangement of the mineral grains rather than how it feels. Okay, so three main factors will influence the texture of an igneous rocks at formation, and those three factors are the rate at which molten rock cools, and this is probably the most important factor of all, the amount of silica within the magma, and then the amount of dissolved gases within the magma. When we consider the rate of cooling, there are some things that we need to think about. So when we consider that first factor, initially, a magma body located many kilometers beneath the Earth's surface remains insulated from lower surface temperatures by the surrounding rock, and thus cooling very, very slowly over a period of time of thousands or even millions of years. Initially, a small number of crystal nuclei do form within this initial melt, and then slow cooling allows ions to migrate freely until they eventually join one of the existing crystals that started crystallizing. So, as a consequence of this, the slow cooling promotes the growth of fewer but larger crystals. Okay? On the other hand, if cooling occurs rapidly, for example in a thin lava flow, the ions quickly lose their mobility and combine with other ions to form crystals very fast, which makes many small crystal nuclei and few remaining ions for further bonding onto the crystal nuclei that have formed. So, this type of cooling inhibits crystal growth. So most crystals are small and many in quantity. Okay? So there's also the possibility for a magma body to start initially cooling slowly, hence making this larger crystal nuclei, but suddenly the magma body is precipitated towards the surface, meaning it flows rapidly towards the surface in some sort of eruption, and the cooling rate increases dramatically. So that makes the remaining of the magma that is still liquid to form and cool very rapidly and crystallize very rapidly. So in this type of scenario, we have two rates of cooling, one that was slow and then the other one that was fast. So we have a mix of large crystals, typically surrounded by a mass of tiny interground crystals, like you're seeing here on the bottom. So again, typically, if the rock is intrusive and it had a lot of time to cool, the crystals are formed as very large and they kind of interlock each other. When the rock cooled very rapidly, so typically when it cooled at the surface, the crystals are very, very tiny and the whole meshes, I guess, of tiny crystals. And then we can have a mixture of the two when we have two rates of cooling, where we have large crystals surrounded by the mass of tiny interground crystals. So, in addition to a magma cooling slowly or fast, it may migrate to a new location or erupt at the surface before it completely solidifies. This results in many types of textures, including aphanitic, meaning fine-grained, phaneritic, coarse-grained, porphyritic, which has two main crystal sizes, one being large, one being small, vesicular, which has gas bubbles in between the crystals that are typically fine-grained, glassy, which has a glassy appearance and texture, a pyroclastic, which contains fragments of other rocks or fragment materials that kind of swim and are just surrounded by these tiny crystals in a mass of them, and also pegmatitic, with very large crystals. In the next few slides, we'll go through each of these different textures in more detail. So the first texture that we'll look at is aphanitic texture. Here the rocks cooled fast. They are typically extrusive rocks. As a consequence of fast cooling, the crystals within the rock are typically very small. And by that I mean small enough not to be seen with the naked eye. So they can only be seen under a microscope or some sort of machine that looks at micro sizes. You can think of aphanitic texture as an analogy to what flour kind of looks like, as if flour were to be solidified. So this is an aphanitic rock. The specific rock is basalt. And then this is how the crystals look under the cross-polarized light of the microscope. Next texture here is phaneritic. So rocks with this type of texture typically cool very slowly, and consequently the crystals that make them up are large and visible to the naked eye. So they tend to be somewhere between 1 millimeter and 4 millimeters in size. These rocks tend to be intrusive in origin or plutonic, and they look as if though the crystals kind of interlocked one another, as if they were kind of in a puzzle. The analogous food that I kind of picture for this type of texture is something like a granola bar. This texture, the porphyritic texture, in this case we have two different rates of cooling associated with it. The first cooling is slow and it forms some very large crystals or relatively large crystals. And then there is a fast cooling that makes up the small crystals that surround the bigger ones. So these smaller crystals make up what we call the matrix or the ground mass. Okay, matrix or ground mass is what these small crystals make up. And the larger crystals that are visible to the naked eye and are kind of swimming on top of that matrix are called the phenocrysts. Okay, and it's spelled there on the slide for you, phenocrysts. Okay, so they are typically, this type of textures are typically volcanic, but they started forming as if they were plutonic. Again, because the large crystals formed under slow conditions, but later there was some event that caused the rest of the rock to crystallize very fast. They must have erupted as volcanic rocks. The analogous food for this type of texture is something like a chocolate chip cookie, or maybe a chocolate chip and raisin cookie, if there are different types of phenocrysts inside of that matrix, like the case on the left over here. So this texture here is pegmatitic. This texture is characterized for having very large crystals. By very large, the crystals must be of 1 centimeter or more at least. This type of texture forms when the rock cools very, very slowly and when there is no restriction usually in the time or the space for the crystals to continue their growth. So this is certainly an intrusive type of rock. All pegmatites are felsic in composition, and they usually occur as veins, which are mineralized spaces where there used to be empty fracture space, but now have been mineralized with the different elements that cooled and crystallized within those spaces. Sometimes some valuable minerals are found within the pegmatites, like gold or silver, and they are usually found as accessory minerals, those ones that are found within the pegmatites. So by being accessory, that still means that the abundance still only 2% or less of that of the host rock. We'll look a little bit more at pegmatites towards the end of the chapter lecture. The pyroclastic texture shown in this slide is characterized by not having crystals that are visible to the naked eye, making up the matrix, and by having fragments that are made up of wood, previously existing rock, bones, or whatever other fragments are found, not from the magma chamber. So these fragments have been incorporated within the matrix at the time of the eruption, or very soon after the deposition of the material that makes up the matrix. But again, prior to the solidifying process, so that they can still be incorporated within the matrix. So it's important to distinguish again that these fragments did not come from the magma body, but that are from elsewhere. Typically, they're fragments from things near or at the surface, like the things I mentioned. Previously existing rocks, bones, wood, yeah. So by now you should know how this type of texture is volcanic rather than plutonic, because obviously there had to be an eruption for those fragments to be incorporated within. Vesicular textures are characterized for having lots of empty spaces surrounded by a fine grained matrix. They're also named porous rocks. A pore is an empty space, basically, where gas cavities used to be within the magma body. These type of rocks are usually extrusive or volcanic rocks. So the way that these gas cavities come to appear within the sample is prior to eruption of the magma inside of the magma itself. So when the eruption starts to occur, everything is so fast that the gases or volatiles, if you guys remember being part of the gaseous part of the melt, can't escape, or not all of them can escape prior to the cooling and the crystallization of that magma, or lava, I guess, because they are volcanic. But due to the high pressure inside their gas cavity, they don't get filled either during the crystallization. So they try to escape, but because of the different materials around them, they can't escape. But because of the pressure inside them as well, no crystals can intrude within the gas cavity. So all of the rock ends up crystallizing with those gas cavities still trapped inside of it. The last texture that I have here is glassy. So this type of texture is characteristic of fast cooling and extrusive igneous rocks. They have no crystals visible to the naked eye, and it forms when molten rock is quenched or cooled very rapidly. And this happens when unordered ions are frozen in place. This type of texture is characteristic of obsidian or dragon glass, as some of you may know it by. And it is high in silica content despite its color. So when you cut it really thin, you can perceive how transparent it really is.